So for video 2, we're going to look at how to solve exponential equations if they have common bases, and we're also going to look at how to solve exponential equations graphically. The common basis technique is really a contrived situation, but it's good to do. It's a good exercise. Solving equations graphically is nice to do because it gives you a way to check your work once you learn how to solve exponential equations via manipulation. We don't have the tools that we need to solve exponential equations via manipulation yet. To do so requires the development of logarithms, and that's a future topic. So for now, we're only going to be looking at two ways to solve the equations. One is going to be kind of contrived setting where bases match, and the other way is going to be graphical solutions. And the idea behind solving an exponential equation if we have common bases is really simple. The idea is if I have a common base, so in this case I have an exponential expression that's base 3, a base 3 exponential expression. Here's my x in the variable position. Here I have a base 3 exponential expression, and I have the two expressions set equal to each other. And the idea is that if the bases are identical, which they are, we have base 3 exponential expressions, then the only way for the two sides to be equal is if the exponents match. So I need 2x to equal x minus 1, and now I can use algebra. I subtract x from both sides. I get x equals -1. And then my check on the work is to plug the -1 into both sides. That went off to the future, didn't it? So plug -1 into both sides, so we get 3, this is my check to make sure I did it right, 3 to the 2 times -1 equals 3 to the -2. And if I plug -1 into the other expression, I get 3 to the -1 minus 1. -1 minus 1 is -2, 3 to the -2. I see that I get the same result on both sides, so my work checks. In the second example, what we want to notice is that we have an exponential expression on the left side and an exponential expression on the right-hand side. We have the variables in the exponent position, but the bases do not match. And so the idea here is we want to see if we are able to rewrite the two expressions so that the bases do match. And what we want to recognize is that 1000 on the right-hand side, which is being raised to the x power, 1000 can be written as 10 cubed. 10 times 10 times 10 is 1000. And 100 over here, which is being raised to the x plus 2 power, can be rewritten as 10 squared. 10 squared is 100. And now I'm in a situation where I have an exponent being raised to another exponent. So I know that I can simplify those by multiplying the exponents. Equals 10 to the an exponent times an exponent. Here I have a 3x. And now I want to look at this and say, aha, now the bases match. I have a base 10 exponential expression on the left-hand side. I have a base 10 exponential expression on the right-hand side. And the only way for those two exponential expressions to be the same is for their exponents to match. So I need 2 times x plus 2 to equal 3 times x. And now I just have a linear equation in a single variable, so I use techniques from algebra to solve. Distribute the 2, subtract 2x from both sides, and that's going to leave us with x equal to 4. And again, if you wanted to check your work, you would take this 4 that you think is the answer and plug it into each of the two exponential expressions up here. So I could take the 100 and replace the x with 4 plus 2, which is the same as 100 to the 6th power, which is going to be a 1 with 6 pairs of 2 zeros after it. So 6 times 2 is 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or a trillion. And then the other one, we'd get 1000 to the 4th power. 1000 to the fourth, which is going to give us 4 sets of 3 zeros following a 1. So if we get 4 sets of 3 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 sets of 3 is 4 times 3 is 12 zeros. 1 with 12 zeros out of it or a trillion. I get the same thing either way, so the answers match. So final example for common bases. So here we have an exponential expression on the left-hand side, an exponential expression on the right-hand side. The bases clearly don't match. However, 9, which is being raised to the 4x power, can be rewritten as 3 squared, and 27, which is being raised to the 2x plus 4 power, can be rewritten as 3 cubed. I have an exponent being raised to another exponent, so I can simplify that by writing 3 times 2x plus 4. We multiply the exponents. 3 to the 2 times 4x is 8x, and now the bases are the same. I have 2 exponential expressions being set equal to each other, each of which is base 3. That means that the exponents need to be equal. So we get 6x plus 12 equaling 8x. Subtract 2x from both sides, and then divide both sides by 2, and we get x equal to 6. And again, we could plug that 6 in and check our work if we wanted to. So that's solving exponential equations with common bases. Now we want to take a look at solving exponential equations graphically. And then, so here we're being asked to solve the equation e to the x plus 1 equals 2x plus 4. So on the left-hand side we have an exponential expression, and on the right-hand side I have a linear expression, and I want to know when these two expressions intersect with each other if we graph them. So the idea is, and notice here we're being asked to round to the nearest hundredth. So the idea is, let's keep that. Let's sneak into GeoGebra, as we just want to graph the two sides. So I can take GeoGebra and open it. I'm using, again, GeoGebra Classic 5 is my tool of choice. I know a lot of you didn't have graphing calculators before the virus put us all in quarantine. So GeoGebra is a great tool because you can download it, and it is free. GeoGebra Classic 5 installs to your computer. I like it better than the other versions that are browser based. I think you should do GeoGebra Classic 5 or 6 is okay as well. So the idea here is I'm just going to graph the equation. So in GeoGebra, need to get my pointer back. There we go. So in GeoGebra, I'm going to take e to the x plus 1, and I'm going to type it down into the input bar down here. So I'm going to type it into this input bar. So I'm going to do e, and then we're going to use the little caret button, and then I need to put the exponent in parentheses. The x plus 1, which is the exponent, needs to go into parentheses, and I just hit enter. And GeoGebra automatically assigns a function name to it. I could explicitly assign a function name. So for example, I'm going to graph the other side now, 2x plus 4. So if I want that to be g of x, I can type in function notation g of x equals my 2x plus 4 and hit enter. So I can either assign the function name or have GeoGebra assign it for me. So once I get the graph, what I'm looking for is the intersections of the graph. So in GeoGebra, it's really easy to find intersections. You can, there's a couple ways. You can kind of cheat and just use the draw a point tool. And if you hover over an intersection, GeoGebra usually guesses that you're trying to mark the intersection, and it will drop a point on that intersection. The other way that you can do it in GeoGebra is to actually use the intersect tool, which if there's multiple intersections is probably the most efficient way to do it. And you can either come into the graph window and select the equations physically, or get your intersect tool, and then come into the algebra window and just click on the two equations. Notice that it has only given me one of the intersections, and I had to do it twice to get the other intersection. Or I could have gone in and selected two. Sometimes it'll give you both. I haven't been able to determine why it sometimes gives you all of the intersections all at once, and sometimes it doesn't. So again, the idea here is we were looking for the x value. So we've got ordered pair intersections sitting here. Got ordered pair intersection sitting here. And we don't want the y coordinates, right? The y coordinate is garbage. This is the point A and B. This is the point A is the one with the negative input. This is point A right here. This is point B. And the y coordinates aren't what we're after because we were looking for x. So that's going to be the negative 1.77 and the 0.68. So we would just need to report those two numbers as our solutions, two decimal places because it's said to the nearest hundredth. So again, the solutions are sitting right here. I have my GeoGebra set up so that it isn't displaying the labels. If I click on these points and right click, I can ask it to show label so that it corresponds to the B over here. And I can actually go into object properties right here, and we can have it display the ordered pair right on the point if that's something that we like to do.